All right, so let's continue on to the multi-cycle architecture. To be honest, I did make some slides here that it's kind of like a repeat of the same thing, so I might skip over some of the slides but I'll make sure it's still it's like consistent with what I want you to talk about. All right. Again, recap. How do we process an instruction, right? Basically, what we need to do is to fetch, get the instruction from the memory, then decode, then get the operand so that we can execute them, and then we write the result back. All right. Again, we always have to go back to these steps because that's fundamentally what needs to happen. Then we'll move to the next instruction. So now let's go back to the toy example, right? In here, if we want to use multi-cycle architecture, the next thing we're going to do is to maybe slowly analyze what can go on and why would multi-cycle be maybe a better solution here, right? So let's assume that when you go and access the memory, this takes one cycle. And definitely not true, right? This is a magic memory that takes one cycle. Modern day DRAM would take around 50 cycle, I would say on average. So it's definitely longer than this. So decode also take one cycle, update the program counter, update the instruction register, take one cycle. Writing to the register file also take one cycle, and every single ALU is also one cycle. All right, basically everything is one cycle. Now let's go back to our toy example with the add R0 and R1 to R2. Basically, we add the number. The first thing I do, I fetch, right? Again, accessing the memory take one cycle. Decode and getting the operand take one cycle. Adding take one cycle. And what I say is writing to the register file take one cycle. And then updating the program counter also take one cycle, right? So how many cycles does it take to run this whole thing? One instruction. How many cycles does it take? From the single cycle architecture, where everything takes one cycle, but I mean, obviously that one cycle is going to be super long, right? Now, just adding, it's going to take how many cycles? Yeah, I'll leave a little bit more time as I see people are typing. So maybe 5 cycle, right? If you look at this, everything I do is 1 cycle. So let me ask you a quick thought question. Let's say this is action A, action B, action C, action D, and action E. My question is, can I do D and E in parallel? Can I do them together at the same time in one cycle? D and E. Well, the thing is I can, right? Because, I mean, if I want to optimize, basically, if I want to optimize, I mean, I can say, hey, I will update the register file at the same time as I update the program counter. Again, sorry about this. Keep having this bug. I need to basically update the diagram. Basically, this allows me to spend 4 cycles and I'm done. 4 cycles. Can I do another optimization? Can I do B and C in parallel at the same time? Here you can see that C depends on B, so you cannot do that. B depends on A, so you cannot do that. D and E depends on C. So you can also cannot do that. So over here, you can either spend 4 or 5. If you don't want to optimize anything, you spend 5 cycle. Otherwise, 4, right? But because the clock is much faster, in here, adding numbers together might take less time, right? Let's go with the same assumption, right? Multiply. Are we basically doing 4 cycles again? Here. Assuming that ALU, regardless of the type, is 1 cycle. It's going to be 4 cycles as well, right? I mean, the same thing. But in reality, multiply is longer compared to add, because add is faster. It's basically simpler action, right? So let's say adding is 1 cycle. Multiplying is 2 cycle. In this design, then my multiply from 4 cycle is going to expand to 5 cycle. But still, when I want to add 2 numbers together, add 4 cycle, multiply 5 cycle. If I stick with single cycle architecture, I need to support add and multiply. The amount of time that I spend in 1 cycle will be longer than adding in multi-cycle architecture, because I need to make sure multiply also finish in 1 cycle. But here, when I break down the cycle count and allow multiple clock cycle per instruction, this means that if I want to finish a multiply, I might take 5 cycles, but that's okay. Because if I want to do an add is faster, it takes 4 cycles. So now I save time. Because my clock is faster. All right. Any questions so far? ถามไหมครับถามภาษาไทยได้นะตอนนี้ถ้าถามภาษาไทยก็ได้นะครับ Now, this is where the slide that jumps a bit happen, because the rest are kind of like the same example over and over again, right? But now let's assume this. How many cycles does it take to assume one cycle memory, 1 cycle ALU? How many cycles does it take to do all these things? From the add example, you saw already is 4 cycles, right? This is another 4 cycles, because again, magic ALU, add is 1 cycle, multiply is 1 cycle, it doesn't matter. Everything is 1 cycle. XOR is also 4 cycles, and the load instruction, if you kind of follow the diagram, is going to be 4 cycles as well. So to finish these 4 lines, how many cycles do I need to spend to finish these 4 lines, 4 instructions? 16, yay. That's when I can tell you don't need coffee yet. At least you can add 4 plus 4 plus 4 plus 4. Now, can I make it faster? We're now transitioning to the concept called pipelining. And this is motivated by this particular observation. Pipelining is the concept behind, if I'm trying to say, let's say I have a set of hardware that have to process things in sequence. And in a multi-cycle architecture, when you're fetching the instruction, when you're trying to fetch the instruction, right? Do I use decoder? Do I use the register file? Do I use the ALU? The answer is not. They're not being used. They're idle. When I'm trying to decode an instruction, the fetch unit is idle. The ALU is idle. I'm not doing anything. When I'm executing an instruction, right, the memory is idle, the decoder is idle. And when I'm trying to basically going through the steps, there are many parts that I'm not using. So my idea, my alternative idea that improve multi-cycle architectures, well, let's say you're trying to doing things in the ALU. Let's say you're adding numbers together. You're now just activating the ALU. Why don't the decoder try to process the next instruction and I use the fetch unit to process the next instruction? Here is how we can use pipelining for exactly that reason. All right, so let's do pipelining 101. Assume that maybe you live in an apartment, right? And assume that you do laundry. มีใครไม่ต้องซักผ้าที่บ้านนะครับหรือว่าก็เคยซักผ้าเนาะทุกคนเคยซักผ้าใช่ไหม So if you have to do laundry, what are the steps that you need to do? Basically, you wash the clothes, then you dry it out, then you fold them. Right? Wash, dry, fold. All right. So let's say you're working on a deadline and you haven't really washed anything for like weeks, right? You basically have to break the pile of clothing that you have right now into say 5 batches because you haven't really do laundry for a long time. You have one washing machine and one drying machine. So one washing machine, one washer, one dryer. All right. And the washer takes 30 minutes to finish while the dryer takes 1 hour. Moving from washing machine to dryer, moving from dryer to just the folding steps takes no time. And when you want to fold the clothes takes 30 minutes. My question right now, how long does it take to finish 5 batches, cleaning 5 batches of clothing? All right, so I'll give everyone some time to answer this question. So how long does it take for me to finish this? And quick note, you have to do things in order. You cannot just do drying, then washing, then folding. You have to do wash, dry, fold. All right. And I'll try to see if there's a pause button. No. All right, perfect. Microsoft Team, awesome. Recording doesn't have a pause button. So what I'll do here, there'll be for if you watch this online after you reviewing the material, there's gonna be a really long awkward silence because I'm waiting for the answer in the chat. All right. So how long does it take to do this? So in the meantime, I'll use the multi-cycle analogy. Yeah. So basically, if you want to do a quick like way to like strategize around this, right? This is like multi-cycle way. Oops. So you're gonna do wash, dry, fold for the first batch, then wash, dry, fold for the second batch, wash, dry, fold, and then wash, dry, fold. Every steps here take 2 hours, right? 2 hours, 2 hours, 2 hours, 2 hours. So in total, with multi-cycle, it's gonna be 10 hours. Question, your time is valuable. Can we do better? Can we do better than this? Can we do better than 10 hours? Yep, exactly. Basically, you first do washing, you wash the first batch, right? Then when the first batch is done, you dry them. In the meantime, the washing machine is free, so the second batch can be in the washing machine. Then when the drying for the first batch is done, you fold them. Now you can dry. The drying machine is now empty, right? Then you can wash the third batch here, which allows you to kind of overlap the time, right? Between these steps. So how long does it take? How long does it take? All right. So this is half an hour, 1 hour, half an hour, right? This again, 1 hour, 1 hour, 1 hour, 1 hour. The first thing you notice is that the drying machine would dominate the time. That's the bottleneck because it's a time, like the most time consuming part, right? So you're gonna have to dry 5 times, right? So that's 5 hours. In the meantime, you just need to wash the first batch and fold the last batch. So that's 1 more hour. So this is basically 6 hours. You save a lot of time, right? You save 4 hours. Now you're back to 6 hours. The execution time is cut by 40%. It's a lot, right? Somehow you run your program in a pipeline CPU and it's getting 40% faster. Magic, right? It's awesome. So in processor design, we can apply the same concept called pipelining. So in the washing the clothes, drying the clothes, and then folding them, the first step is I fetch, then I decode, then I execute, then I access the memory, then I write it back. Write back means that I save the progress and so that I can move on to the next instruction. Now, is the concept clear? Now, my first question is the concept clear? Any questions about the pipelining concept? I'm not talking about implementation yet, all right? Just the concept. All right, so what are the issues? My first issue is, okay, let's go back to here, right? Let's say instruction 1 is executing. Instruction 1 is executing, right? How do I make sure I save the progress that are related to instruction 1 while the decoder is processing instruction 2? And then the fetch is trying to process instruction 3. Because if you think about it this way, instruction 1 is in the ALU right now. Instruction 2 is in the decoder. So it also means that for the operand that you try to get from the register, right? Here, instruction, like this wire, the inputs into my ALU is needed at this moment by both instruction 1 because I'm adding the number right now, and instruction 2 because I'm decoding. I'm just trying to gather my operand. You see the problem? I have 1 wire, but I need to somehow store the older instruction and the newer instruction. Just to make sure I clarify this in Thai language, so I'm gonna switch to Thai a little bit. คือปัญหาตรงนี้ครับก็คือว่าไอ้ตรง adder อ่ะ instruction 1 มันอยู่ใน add execute step ใช่ไหมคือ adder มันต้องเป็นค่า input ของ instruction 1 อ่ะแล้วไอ้สายไฟเส้นเนี้ยที่มันวิ่งอยู่อ่ะของ adder อ่ะมันต้องการ instruction 1 operand แต่ใน decoder ไอ้สายไฟเส้นเดียวกันอ่ะมันต้องการบอกว่าให้ register file ขอ operand ตัวใหม่ของ instruction ที่ 2 เพราะฉะนั้นไอ้สายไฟเส้นเดียวกันน่ะมันจะมีค่าโวลเตจ2 อันไม่ได้มันต้องมีค่าโวลเตจแค่อันเดียวมันต้องเลือกระหว่างจะเก็บค่า instruction 1 กับ instruction 2 ต้องเอาอันไหนได้อันเดียวอันนี้คือปัญหาเห็นภาพขึ้นไหมครับว่าปัญหามันคือจะอยู่ตรงนี้ผมมีสายไฟเส้นเดียวแต่ผมต้องเก็บค่า2 ค่าSo again, the problem is I have 1 wire, but I need to keep information of multiple instructions. So what's the solution, right? The issue again here is I don't have the hardware. I don't have the hardware to store the state, the internal state of instruction 1 when it needs the internal state of instruction 1. I also don't have the internal hardware to store the internal state of instruction 2 and instruction 3 and anything here because I don't have the hardware. So here's the solution. We can then add another set of register because register is just a temp value that I can use in any purpose, right? So I'll add this thing called the pipeline register, right? Because we need to store any intermediate value to save the state of each instruction through the pipeline, right? So adding the register allow you to store the stage that are depending for basically it's the stage that's needed by each instruction. The thing is this can be costly. So when you design a really deep pipeline, so let's say I design a modern CPU with 30 stages, 30 pipeline stages, which is a real thing. We do it this way, right? You need to kind of think about, okay, how much power is going to consume? How do we save the chip area as much as possible? So now, the only thing that changed from this slide to the earlier slide is I changed the dashed line, which is like just the high level separation of the stage into this box, this like long box here, right? This thing. These are all pipeline register. And the way you can kind of think about this box is if I need to have wiring that go across the stage, for example, look at this wire. If my instruction 1 is here, right? Instruction 2 is here. Instruction 3 is here. Instruction 4 is here. Instruction 5 is here. For that one wire alone, this one, right? Let's say this is point A. This is point B. And this is point C. For point A, should that be the result of instruction 1, 2, or 3? Point A. Instruction 1. Then point B, which is, I mean, in theory, it's kind of the same wire, right? Without the pipeline register, that becomes the same wire, but you have to store the result from instruction 2. And for point C, it has to be whatever is coming out of the ALU, which is from instruction 3. Pipeline registers basically deliver this goal for me because now it's a register. So one thing I can do is over here, store basically this store A. This is basically storing B. That's it. We're good, right? Because what comes out of the pipeline register will be the state used by that instruction. So in this way, I can then separate out the output, for example, in this case, the output from the ALU, that is this from this instruction or other instruction, right? Again, this thin red box is a register, so I can use it to store a bunch of value. So I can use it that way, right? And I can apply the same technique on, for example, the data coming out of memory right here and right here. I can use it to separate the operand coming from decoder right here and right here. I can use it to separate out the program counter's value that's supposed to go to the IR right here. That have to be from instruction 1. But then you're fetching instruction 6 in the next cycle, right? So these are the things you can do to make sure you have a pipeline design that still works. Okay. Any questions so far มีคำถามไหมครับถามภาษาไทยได้เหมือนเดิมนะครับ So again, this kind of derive, right, the key issue, which is when you have to handle different instruction in each of the state, right? fetch is instruction n, decode n-1, execute n-2, memory is n-3, write back is the oldest, that's in n-4, right? And again, what programmers see should be just what happened after the write back, okay? After the write back, that's what the programmers see. Register file and program counter has to be updated at write back. So that's one big issue now, right? Register file and the program counter is updated after I'm done with the write back. So here again, the same design with our key issue. Let's say instruction 1 is right here, and this generate R0. When I said generate R0, it means that let's say I'm adding something and write the result to R0, right? I'm writing the result to R0. And the instruction 2 is right here. Instruction 3 is right here. This guy just happened to need R0 that are generated by instruction 1. My question, in the next cycle, can I send instruction 3 to execute? Do I see the updated R0 yet by instruction 1? So over here, right, register file, or this guy is not updated, right? It still have the old version of R0. So I have to wait until instruction 1 finish write back before instruction 3 can move from the decode stage. Because otherwise, if it moves right now, I will have the old version of R0. Repeat this again in Thai just to make sure everyone is on the same page. คือถ้าผมตีต่างว่าตอนเนี้ย instruction 1 ของผมมันกำลังทำอะไรสักอย่างหนึ่งแบบอะไรบวกเลขก็ได้แล้วมันต้องการเขียนผลลัพธ์ไปที่ R0 แล้ว instruction 3 ที่มันอยู่ใน decode ตอนเนี้ยมันบอกว่าเฮ้ยผมจะใช้ R0 นะแล้ว R0 ที่จะใช้มันคือ R0 ที่ถูก generate โดย instruction 1 ในกรณีนี้เนี่ยเพราะผมบอกว่าเราจะไม่อัปเดตไอตัว register file จนกว่า instruction นั้นจะทำ write back เสร็จเพราะฉะนั้น R0 มันจะเป็นตัวเก่าไปเรื่อยๆ R0 ตอนนี้มันจะเป็นตัวเก่าไปเรื่อยๆจนกว่า instruction 1 จะเสร็จจาก write back เพราะฉะนั้น instruction 3 มันจะไปไม่ได้เลยจนกว่า R0 จะถูกอัปเดตแล้วแปลว่าอะไรแปลว่า processor เราช้าลง Basically from this scenario, right, I cannot move instruction 3 until I update my register file, which can slow down my processor. Another thing that you have to kind of design around is how many pipeline stages that we need, because adding more allow you to clock faster. And you can even pipeline within the stage. For example, I can do 3 cycles at 5 cycle multiply, and it's fully pipelined. So I can basically feed in 3 instructions into each of the adding steps. And these allow even higher utilization, allow more things to be active at all time. And generally this makes your CPU really, really fast. All right. Downside, it's going to consume more power, more die area, and more complex to design. What if there's also a branch? Right. So we'll talk about branch in the following weeks, just to make sure we kind of done with pipelining first. So let's assume this one simple example, and let's say with a 5-stage pipeline. Let's do a quick calculation on how long does this take? All right. So you have 4 instructions. Instruction 1, instruction 2, instruction 3, and instruction 4. All right. Each one of these will have to go to fetch, decode, execute, memory, write back. So instruction 1 go to fetch, decode, execute, memory, and write back. Instruction 2 can start here because no one is using the fetch unit. Then I can do fetch, decode, execute, memory, write back. Fetch, decode, execute, memory, write back. Fetch, decode, execute, memory, and write back. And as you can see, this only takes 8 cycles. Okay? It's a lot faster than a multi-cycle architecture. Because in multi-cycle architecture, I need to finish instruction 1 entirely before I start instruction 2. Okay. So now let's go with another example. Now we have this weird scenario where the first instruction generates the result needed by the next instruction. Same here. Then you have R6 that is needed by this guy, R8 needed by this guy. So you have instruction 1 here, instruction 2 here, instruction 3 here, instruction 4 here, instruction 5 over here. All right. So think about it. Are we going to be as fast as an earlier example or not? Or are we going to be a little bit slower? Are we going to be slower here? Or the same speed as the other example? So now let me go through this example, okay? Instruction 1, I can, oops, sorry. I can definitely fetch, right? I can decode, I can execute, I can go to memory, I can do write back. Now instruction 2 comes in, I can fetch, I can decode. Once I decode, I realize that, oh, I need R0. R0 is not going to be updated until cycle number 6. So this is when R0 is updated, right, in the register file. So over here, because R0 is updated in cycle number 6. Cycle number 6 is when you got the correct R0. So you can basically, you cannot move right now because you need to first take the correct R0, feed that into the pipeline register, and then you can execute here, right? So over here, you're not doing anything. You're not doing anything useful here, right? Nothing here. And then execute memory, write back. I can fetch here. I cannot even decode because the decoder is used by instruction 2, right? So this again, stalling. Until I can then use the decoder. When I decode the third instruction, I then realize, oh, I need R3. Again, R3 is available here. R3 is available. So I have to execute here, memory, and write back. Again, more stalling, right? And then I cannot even fetch until here because fetch unit is occupied by instruction 3. I can then decode here. When I decode, I then realize that, oh, okay, for instruction 4, I don't need anything. So I can then wait until the execute unit is not occupied, memory, and write back, which is okay, that's fine. Then I can fetch here, I can decode here. Then I realize that I need R8. R8 is not updated until here. So you can execute, memory, and write back. And as you can see here, there are dependency where you cannot start the next instruction until you finish the earlier instruction. That can slow down the pipeline. All right, that can slow down the pipeline. We call this instruction stall. In this case, there's not enough resource to move the instruction through the pipeline. So the effect is process is going to be slower. The cost can be like we don't have enough functional units, some step takes longer, or some unbalanced design, right? So in this case, we still need to ensure correct results. So we wait. We wait until the pipeline is like basically updating the register, right? And sorry about this, repeat the slide. That's it for the class today. I want to end it with the motivation that even with pipelining, it's not great. It's much better than single cycle. It's much better than multi-cycle architecture, but we can do even better. So next week, we'll talk about the technique called data forwarding that make it even faster. All right, that make your design even faster. I'll stop the recording right now because basically that's it for the lecture part of this this week. So I'll see you on the lecture side, on the online side. I'll see you. You can basically continue on to next week material right now. In the meantime, I'm going to talk about some of the papers we're reading. So it'll be more discussion-based kind of lecture. All right. So